Well, now you're in it. Proof by mathematical induction. Um, Nothing new today. How about that? Except for maybe some trig, maybe some product formulas. This is all stuff you've seen before. Now we just have to kind of remember it. So let's just dive right in. Hey, nothing's changed. We still have two things to do. We have to show that the base case works. The base case is our good friend. We're just kind of checking that out. And then this is, we're going to assume the kth, and we're going to hopefully show that it implies the truth of the k plus first. All right, if we can do that, then we kind of have done everything we need to. Let's go for it. All right, so I have pulled a lot of examples that are just trying to give you a good start. I've given you all the solutions, so these are mostly hints. When we ask, we're given the first term, the second term, the third term, okay? And then here we're told exactly what the formula is for each term. So when we look for finding A and B, we just plug in n equals 1, maybe n equals 2, and try to solve for A and B. Two equations, two unknowns should be enough. That should be enough for you to see my thought process. We plugged in n equals 1, we got this, we knew the first term, plugged in n equals 2, we got this, we knew the second term. I like to work with whole numbers. I multiply the top one by -2 to get that -4a canceled. B equals 4, A equals 3. All right. Not too tough, not too tough. All right. So part B is now this is purely an algebraic thing, and you should try this before you watch this. Let me just get you started. This u sub n or u sub I is the ith term or the general term. That's exactly what we just are working with up here. Okay, now we know what A and B are, so I just wanted to make that connection. That u is this u. Okay, so we have our general term and we have our formation, or what we think is the function. So when we prove this by mathematical induction, we have to start out with the base case, and that's n equals 1. We go nice and slow so it doesn't jump. That's just awesome. All right, base 1. Left-hand side, we plug in a 1, and for the remember, the left-hand side is just this equation. I get 1 through 3. Then plug in 1 into the summation formula, 3. Great. Wow, we are cruising now. I'm just going to get rid of that thing. All right, so now we assume S sub n is true for n equals k. So a different way to saying S sub k is true. So I just trying to mix that up. You're going to see it in different ways. Basically, this is the inductive step. It's called the inductive step. So we're going to use this. That's a pretty cool formula. What do we want to show? Remember, this is kind of like on the sly in the background. It's like keeps you going, moves you forward. Is somehow algebraically get to this. Well, S sub k plus 1 is the sum of the first k terms plus the k plus first term. So I've written all that out right here. Great. And remember, the want to show kind of helps you direct you, like, how should I do this? I have the 3 halves and the 4. I have the 3 halves and the 4. So I'm wondering if I can get these to play without messing those up. So I clean it up a little bit, kind of get these closer. So this is 3 over k to the plus 1, 3, subtract 1. So that's this term, and that is this term now. Hey, verify that the exponents are correct, you know. Now I want to put this into there. And, you know, it's just kind of cool is that I want it in there, but how do I get it in there and not change it? Well, check it out. See how the 3 halves and the 2/3 work together? If I distribute that, I will get the 2/3 to drop out, and I get 1 3 to the k. Little cool trick. All right, so now I'm in there. Now I'm in the game. And I do the same thing with this other term, 1/4 and 4. So those are the cool little things to notice. I'll let you work that out. It works out pretty cool. It gets you to the one you want to show. Life's good. There's the solution if you want to look. My solutions are, of course, better and sometimes hard to read. Sometimes they're exactly the same. Sometimes I do a little different step. So compare and contrast. All right, this is called a recursive formula. Recursive. Why is it called a recursive? Because if I want to get any term, I have to use the term right before it to get it. So just to make sure, they tell us what the first term is. That's nice. So when I have n equals 1, when I plug it into this formula, it becomes u sub 2. So basically, when I'm finding the second term, I plug in n equals 1, so that becomes a 2, and then that becomes a 1, and it's telling me to find the second term. I go 2 times the first term, or the term right before it, plus 1. It's really pretty simple. Well, I know what the first term is. It's 1. Plug it in. And now I know that this is the second term. To find the third term, I go 2 times the term right before it, or u sub 2, plus 1. And I know what u sub 2 is. We just figured that out. That is now plugged in, and I get 7. Awesome. U sub, when n equals 3, I'm finding the fourth term. I need the third term. I'll go to get the third term. I'm good. I want to find the 101st term. So I 2 times the 100th term. Oh man, what? So do you see the problem with the recursive formula is you really need to know the term right before it. So this is a bummer. I got to do a lot of work to get to the 100th term so I can get to the 101st term. Cool little problem. All right, so we get this. We know we have a recursive formula. It would be really cool to have what we call an explicit formula. So this is something I just plug in n. If I want to find the third term, I just plug in 3 there, third term. 2 to the third minus 1. 2 to the third is 8, minus 1 is 7. If you recall, I did not kick it all the way out, but there was a 7 and it was the third term. Boom! So this is a special case for when you're given recursive formula. It works out almost nicer, but it's a little different, right? So first thing, we're going to plug in n equals 1. Do we get the first term? Well, we know what the first term is. It's 1. So we plug it into our new formula, and we get 1. Check. P sub 1 is true. The base case is true. All right. Now we're going to assume P sub k is true. What that means is if I plug in k, I will get the correct number. Awesome. So this is the crux right here. You got to make this work. This is our old formula, the recursive. Why do we use it? Because it got a u sub k in it. That's what our new formula is in. So u sub k plus 1, we're following this right here. Instead of n, we got k, of course. U sub k plus 1, 2 u sub k plus 1. Now we sub. And we get this, beautiful. 2 to the first times 2 to the k is 2 to the k plus 1 minus, yep. And this is exactly what we expected it to be. I didn't do the want to show. If I did do the want to show earlier, I would have plugged k plus 1 in here, gotten 2 to the k plus 1 minus 1, and that's certainly what we got to. Gosh, I hope you're starting to make sense of this. This is new though. This is this recursive. It's these 3 steps that's all you have to do is get u sub k plus 1, get that u sub k in it, and then substitute. Works every time. All right, 20 I've seen on an IB exam before, basically, so I thought I'd walk you through it. I think it's a little bit challenging to understand. Especially after the chapter we just did, a sub n. So what they're saying is plug 1 in and see if you can find out what a sub 1 is, what b sub 1 is. I think for n equals 1, it's really easy. A is 2 and b is 1. It's really easy. But when n equals 2, then you got a 2 there. These are subscript 2. We do a little multiplication. We get something plus something times the square root, and we compare coefficients. So everything in front of the square root is B2, everything else A2. So that makes our identification pretty easy. Now, I'm going to show you what we do for 3. N equals 3, we have this, great, but we're going to rewrite it as the one just less and multiply it by that. Why? Because didn't we just do all the work? 7 plus 4 times the square root of 3? Yeah, so now we just have to multiply that out. We don't have to start. What I'm not doing is the binomial theorem. And that is actually important for later on. So if you adopt that process, you kind of get the flow of things. So for obviously n equals 4, we take it to the third power times 2 plus square root of 3. We'd use our answer from the one previous and multiply it out. All right, part B. Part B asks, is there a way for you to show this and show this? If you adopt that process in A, you can see that that's kind of what we're after. Where are we going to get those coefficients? It's if we take this to the n plus first power. But that's the same thing as taking this to the nth power times it one more time. But we already know the coefficient of the nth power. It's a sub n and b sub n. You're like, no, Mr. Sayers, I want a number, I want a formula. Me too. That's why I had to work on this problem for a little bit longer than I wanted to. But that's exactly what we're after. Then we multiply this out. We get everything without a square root, boom, and we get everything out without a with a square root together, and we get as desired. If we go back up to B, that's the equations they gave you. So show means that should be your answer. Let's say you can't get it. Well, maybe, just maybe, you might use that later on in C and D. Okay. So part C, they're saying calculate this for n equals 1, hence conjecture result. Well, I'm just like, what? Plug that 1 in. I know what A and B are for A sub 1 and B sub 1. We did that in part A. So I plugged, and I got 1. Neato. A sub 2 squared, I remember I got a 7 and 4. And ooh, a 1. Well, work them all out. I'll bet you get a 1 for all of them. So maybe, just maybe, this is your conjecture. A sub n squared minus 3b sub n squared is equal to 1. Awesome. Well, let's go prove it. So if that's what we want to prove, once again, it's to the nth, so maybe proof by induction. What do we know? We know that from part B. I just wrote it. I don't know if I need it. Base case. Did it work for the first one? It did. We already showed that actually for n equals 1 in part C, but for kicks and giggles, go ahead and throw that out. All right, P sub k is true, so I'm going to say that this happens. What I want to prove is a sub k plus 1 squared minus 3b sub k plus 1 squared is equal to 1, and it would be sure cool if we used this in that. So let's look at what that is. Boom. Oh, but wait a minute, don't we have this in terms of a sub k and b sub k, and this in terms of a sub k and b sub k? We do. From part B, plug it in, we square it, we get a bunch of stuff. So we're going to work through this knowing this is what we assumed. So we kind of, if we get that somewhere in here, if we multiply all this stuff out and somewhere there's that, I can substitute in a 1 for that. And what we want to show is we get this all equal to 1. So I'm going to leave that up to you. Good luck. There's your answer if you have to have it. Whoo, man. This, all of a sudden, sine and cosine are not off limits, all right? And all their properties and all their doubling of formulas. So I'm just saying, get your formula sheet out and get ready because you're going to need it. And this is a little painful, but know that it's finite. It's finite. Once you see it once, twice, three times, you're going to know there's only 4 or 5 things that you just got to have at your grasp. All right, pretty cool looking formula. Um, didn't know this. I didn't know if you added this up, that's what you'd get. That's great. So we kind of have this proposition. We think this is true, and we want to prove it. This is where proof by induction is beautiful. There's 2 things you need to prove: base case, assume the kth is correct. Can you come up with the k plus first? All right. So if n equals 1, the first term is that. Plug a 1 in, and what we got to show is that's equal to 2 cosine 2x. Oh my. We need to prove that this is equal to 2 cosine 2x. There's not even a cosine in it. All right, and no, you cannot subtract the 3x from the x. Don't even think that. Stop it. You see? You see what I'm doing this? I'm helping you out. All right, so what are some things that we can think about? 3x can be written as 2x plus x. Why is that good? Because maybe you recall sine of a plus b is equal to something. Maybe. You just got to start somewhere, right? So that is the double angle formula. And for some reason, I got these backwards. The next slide kind of has this in front of you. So that's my A and that's my B. If I do this, sine A cosine B plus cosine B sine A. Beautiful. Can you see a 2 cosine 2x in here? I see a cosine 2x here, like, I don't know. I like the minus 1. No, I don't. I don't like the minus 1 at all. There's no minus 1 in this. Dang. So at this point, maybe the best thing that you can do is try to figure out what happened. How did they get from here to here? You know, and that's when if you're looking at the solutions, that might be your best thing. Sine of 2x became 2 sine cosine x. That's a double angle formula that you know what, you're going to get familiar with. Just like cosine 2x is a formula. So once we get a sine x on both terms, we can cancel out that denominator. That's pretty cool. You know what? I'm just going to get rid of that sucker. I hate it. All right. So we are now at this to this. We got the cosine times the cosine. That gives us 2 cosine squared. We got the cosine x minus 1. All right. They put this with this to show you something. That is cosine 2x. So now we have cosine 2x plus cosine 2x. When you add those, you get 2 cosine 2x. So what do we kind of learn here? We really need to remember what's sine of 2x equal to and what's the cosine of 2x equal to. We use this a lot when you're integrating because nobody likes to integrate cosine squared. So there's a substitution of cosine 2x and all of a sudden the integral goes a lot better. So that's probably the last time you saw it. That was base case, huh? How long is it base case taking that long? All right, as you can see, this is blue, meaning this is an example in your book. I kind of changed, I took out a line here and wrote some stuff. But please, listen to that video. Maybe they use some verbiage that I don't. So when we're looking at a summation, I like to, we've made this assumption that S of k is the sum at k. We know the next term of this series, if I plug k plus 1 into this kind of general term, I get this. So the first step is we got this over sine x. We're going to get common denominator here. The -1 just kind of floats back out here, and we're left here. All right. So, whew, this is tricky. This, nothing changes. Great. This, we have, here's that sine x and the cosine. If you think of this quantity as your A and this whole quantity as your B, then you can do a really cool identity, and that's this one. So I don't know why they wrote it down here, but from going from here to here, they see the 2 sine A cosine B. 2 sine A cosine B can be rewritten as sine A plus B plus sine A minus B. So here's your sine A plus B, and here's your sine A minus B. Wow. Okay. No, you're not going to be able to do this just by like, oh, I think I'll do that next. What you're trying to think about is what you want to show. And what you're trying to do here is kind of boil some stuff down. You need to get this, you need something to cancel. So maybe by breaking it up like this, something will hopefully cancel. Let's see. This is kind of a miraculous step. From here to here, what they did is they distributed the -2. So you got -2k minus 2 x. The minus 2x plus the x becomes a minus x. And then they factored the x back out. So, and the negative. So that's where you get this. Holy mackerel. So this becomes this. I challenge you to just, show your steps and get there. Why do they want this? Because when you have sine of negative theta, you can pull that negative out front for sine, only sine. So that negative comes out here, and that makes it the opposite of this term, so those cancel. Wow. Are you kind of leaning back going, there's no way? There is a way. You just got to work through a few. And I'm not saying that you're going to come up with this in the heat of the battle in May, but you're not going to be scared of it either. You got to know there's a few things that you can bring to the table. All right. Then you end up right there. That's what we wanted to show. And so we're done. So it was some really tricky trigonometry that did that for us. Hey, 23, obviously I should have done this one before. I don't know why. I kind of talk about, this is what's given in your formula packet. That formula that we just used wasn't there, but sine of A plus B, if I'm looking right here and I do sine of A plus B, notice the plus is on top, so I use a plus right there. If I do sine A minus B, the minus is right here, the minus is right here. But if I just add those two, on the left-hand side, I get the sine of A minus B plus sine of A plus B, so I've added those. Over here, this cancels this, and I'm left with this. So this is the form that they had. They had this, and they rewrote it like that. So it's not like magic, but it is kind of a pretty advanced technique. Oh, back. I think I wrote something down here. Oh yeah. So for example, if you had x is equal to a, or this, you think of this quantity as your a and this quantity as your b, you can rewrite it as them being subtracted and them being added. So it would end up with this. So you could write this instead of 2 sine x cosine 3x. X plus the 3x is known as 4x in some circles. All right. Oh, look at that. Maybe we're about to use this. So on 23, I would work through it and understand that, they're using this for the second time. Oh, the second time. Does that mean there might be a third time? Well, that's up to you. It's kind of relentless right now. It's the same idea. Base case, assume piece of k, show piece of k plus 1, but you got to know what the notation is. I don't know if any of you have seen this before, but this notation means take this term and keep multiplying it. So there's no addition sign. So this means the product of terms. We're used to sigma meaning the sum of terms. Okay, so if you know that, maybe you can do this. Base case, plug in a 1. Do we get left side equal to right side? We do. So what is the piece of k? Piece of k means piece of k means we're going to assume this is true. We're going to plug in a k there. We think that the first k terms multiplied gives me this. Well, if I want the first k plus 1 terms multiplied, I'd multiply the first k terms times the k plus first term. Okay, I'll let you take it from there. You're going to just multiply some stuff out. Life's good. You can look at my notes. There's the answers. All right, final thing. We want to prove this is always less than this for every value of n. So this is inequalities, and wow, this is, I love this because talk about the audacity to do such things. All right, first thing, base case. Plug in 1, and it turns out that 1/2 is less than 1, and that is true. So now we go to the second. We're going to assume that piece of k is true. So we are now saying that 2 to the negative k will always be less than 1 over k. All right, so this is our goal. This is our want to show. This is what we want to get to. And so here we go. So I'm going to write 2 to the negative k plus 1, and I know that's equal to 2 to the negative k, 2 to the negative 1. Remember what I want. Okay. I'm going to substitute in 2 to the negative k is less than 1 over k. Now when I do that, I'm plugging in, this is equal. So if I plug in a number that I know is less than 2 to the negative k, this is no longer correct. Okay, I'm not going to say it's equal to, whoops. I'm going to say it is now less than. Okay, so that's really important. If I'm plugging in something bigger than what was there and it was equal, then that makes this side bigger. And we know k is a positive integer, so we don't have to mess around that. Nice try. All right, did we get what we wanted? Are we there? Did we get it less than 1 over k plus 1? No, darn it. So let's multiply this out so we know this is true. I really wish this was k plus 1. Maybe I made a mistake. And that's what is so hard about inequalities. I can substitute 1 plus k, k plus 1, and know it is still going to be greater. Why do I know that? Since k is greater than or equal to 1, we know that k plus 1 is going to be less than 2k. Okay, it has to be. But if you stop, if you're like, okay, but how do I, if it's less than, I don't, so, but think about it, that means 1 over k plus 1 is going to be greater than 1 over 2k. Because once you do 1 over, the bigger number becomes kind of a smaller number. All right, so if we had 1 over 2k before, if we plug in something that's bigger than that, then it's going to stay bigger. So that allows us to make that substitution. So this is the challenge of inequalities, is that you need to choose something there. I am not even going to go over this. We have a lot of work to do. Good luck. This is going to require a lot of patience and questions. And I'm going to build you up. I want to work you hard for a couple days, and then I'm going to show you some IB questions, and you're going to be like, wow, I got this. And I know you will. So keep working hard. Thank you.